Hi, Ravi. I've decided to lay everything out there and not try and review things slowly. It took too much time.
So theoretically, for every finite index subgroups of triangle group, there should be graphs and this dasa. But which methods would be the most easiest one? That is the question. And for computational things, these are the problems in this area actually. So do you think this Ferre symbol and this method of modular group is better? Because
I think we should let us listen to him.
Actually, I can't hear you very well, so I didn't quite get the question.
okay, let's talk after the talk.
Okay. Sure. Yeah. Yeah, maybe after the talk, I can use my earphones and I might be able to hear you better. Yeah. Should I start?
Let Krishnendu. Krishnendu, are you there?
Yeah, I'm there.
Okay, maybe you can.
I think we are still
announce.
1 minute to go, so let's 8:30 we can start, no?
1 minute, yeah.
By 5:29. Okay, so just wait for a minute.
Your voice is not clear, Krishnendu.
So now is it clear?
Yeah, now it is.
Okay. Okay, so I think it's 5:30 at my clock.
Yeah, everywhere.
Yeah. Okay. So welcome back. So Professor Tan will continue his lecture. So in the first half, you saw about some basic geometry of the modular group, and now he will describe the algebraic aspect and connect the two. So Sir, over to you.
Thank you. Okay. Thank you. I took a lot of time earlier, so I'm going to try and speed up a little bit, but I still want to make sure that it's relatively clear. So I'll try and emphasize the important things anyhow. Okay. So like I said earlier, everything was geometric, but we really want to do. We really want to be able to do some calculations, right? So let me just recall. For the modular group, the set of Cusp is all of the rational numbers. And then if I have a rational number, then there's a reduced form, right? That means the GCD of P and Q is equal to 1. And if we normalize further to make Q to be greater than or equal to 0, then the reduced form is unique. Well, of course, infinity has sort of two reduced forms. Okay. Besides this, maybe a slightly less well-known fact is that we can generate all of the rational numbers by using Ferre addition, right? So for example, you start with 0 over 1 and 1 over 1, then you take the sum of the numerators and denominators to get the midpoint, to get half, and then you keep doing this, and then you can get all rational numbers between 0 and 1. Okay. And this is also how the Ferre triangulation can be drawn. So we want to generalize these two ideas. First, the idea of a unique reduced form, and second, the idea of how to generate the cusp, okay, in a algorithmic way, okay, to GQ, okay. So let me just remind you that another way to say that the PQ is equal to 1 is to say that there exists S and T such that PQ, the matrix PQST is actually has determinant 1. It's inside the modular group, right? So this is I'm saying this because this is what I'm going to use rather than saying that the two of them have great GCD1, because in the case of the Hecke groups, the GCD is not so well defined. Okay, so here's the definition. is a simple definition. If I have a cusp, then we say that this is written in the form A over B, where A, B are inside the integers, is in reduced form. If we can find two other integers C, D in Z lambda Q, such that A, B, C, D is inside GQ. So and secondly, a normalization, it is the B is bigger than equal to 0. Okay, so this a definition. So the first lemma we're going to prove is that the reduced form for any non-infinity cusp is unique. Okay. So the proof is again quite simple. Suppose I've X has two reduced form A over B and A prime over B prime. That means that I have two matrices A, B, C, D and A prime, B prime, C prime, D prime inside GQ. So then if I take the inverse of one multiplied by the other one, it should be an element of GQ which fixes infinity. But the elements of GQ which fix infinity are of the form plus minus 1, M lambda Q 0 plus minus 1. Okay. Because the stabilizer of infinity is generated by 1 lambda Q 0 1. Okay, so you just bring this over to the other side and then do multiply things out, and you find that in fact A prime is equal plus or minus A, B prime equal plus minus B. The normalization that B is bigger or equal to 0 means that A is equal to A prime, B equal to B prime. Okay. So the proof is quite simple. Okay. But it justifies our definition in some sense now. So having said that, we go to the second problem, which is how do you find the reduced form of a given cusp? Okay. So we're going to generalize this idea of the Ferry construction, the Ferry addition that is used to construct the Ferry triangulation. Okay, so as I said, we have two Q-gons which are closest to I, and then after that, successive Q-gons are further away. Right? Okay, so you can use the cuboid tree to define this distance. And then the line from 0 to 1, there's the reduced form is 1, 0, 0, 1 or minus 1, 0, 0, minus 1. Okay, so we're going to use an induction. Okay, so suppose that I have an ideal Q-gon x1 up to xq, and suppose that we know the reduced form for x1 and xq. Okay. Then I define x0 to be the reduced form for x0 to be minus aq over minus bq. And then I can find the reduced forms for all the other vertices, x2, x3, and so on. The formula is very simple. AI is equal to lambda times AI minus 1 subtract AI minus 2. BI is equal to lambda times BI minus 1 subtract BI minus 2. Okay. So it's just is this clear? I mean, this is not important. I just want to emphasize over here that we know the reduced forms for two of the vertices, and then we can generate the reduced forms for the other vertices in the ideal polygon by this very simple rule. Okay. I mean, you put this in a computer, it just does it in no time. I mean, you can even do this by hand, obviously. But remember, of course, lambda is an algebraic number, so it satisfies some equation. Okay, so let me explain why this is a generalization of the Ferry addition. So in the case of G3, right, we know X is a cusp if it's a rational number, and then if I have three vertices of an ideal triangle, okay, in the Ferry tessellation, then I'm assuming that I know the reduced form for x1 and x3, right? Okay, because this line is sort of closer to I than the other two lines. Okay, so I know. So this was actually the side of an ideal triangle, which actually whose reduced forms were really determined. So how do I determine x2, right? Well, what I do was I had x0 is equal to minus a3 over minus b3, right? Then x1 is a1 over b1. Then x2, okay, so the a2 is equal to a1 lambda a1. In this case, lambda is equal to 1. Subtract minus a3, so it's a1 plus a3, and then b2 is equal to lambda b1, which is just b1, subtract minus b3, which is b1 plus b3, which is exactly the Fourier addition. Okay. So if lambda, so in the case for G5, okay, the case for G5, it's quite workable because in this case, lambda satisfies this quadratic equation, lambda square is equal to lambda plus 1. And by Lloyd-Becker, a result of Lloyd-Becker, any rational number in Q lambda is a Cusp. So in particular, we can find reduced forms for any rational number. So I'm just giving you the answer over here. The reduced form for 1 is not too bad. It's actually just equal to lambda over lambda. So I just remind you that lambda is actually a unit inside Z lambda. Because on the other hand, the reduced form for 21 over 34 is actually very complicated. And it looks really complicated in this form, but actually if you look at it over in this way, it's just 21 times lambda to the 36 over 34 times lambda to the 36. So in particular, in some sense, the GCD of the numerator and denominator is still equal to 1. Because remember, lambda is a unit in this case. Is that all right? So, I mean, this is not obvious, but you can sort of do a computer program and go downwards until eventually you reach the Cusp 21 over 34, and you find that its reduced form is actually equal to this. Okay. So here I give an example for the first case. In the first case, the reduced form for 0 is 0 over 1. The reduced form for infinity is 1 over 0, which is x5. So I write x0 as minus 1 over 0. Then to get x1, to get x2, I get lambda times 0, subtract minus 1. So lambda times 0, subtract minus 1, it's lambda times 0 plus 1 for the numerator. Denominator is lambda times 1, subtract 0. So numerator now becomes 1, denominator is lambda. So this is x2. To get x3, a3 is given by lambda times 1, subtract 0. And then b3 is given by lambda times lambda, subtract 1. So you get lambda over lambda squared minus 1. But remember, lambda squared is equal to lambda plus 1. So this is actually equal to lambda over lambda. So this thing here is actually equal to 1, right? So this is how you can see that the reduced form for 1 is actually lambda over lambda. The next one is x4. x4, you take again, you take lambda times lambda minus 1 over lambda times lambda minus lambda. And then numerator becomes lambda squared minus 1, denominator is lambda squared minus lambda, which is lambda over 1. So the reduced form for x4 is lambda over 1, which actually we know. Okay. And so once we know, for example, x1, x2 in reduced form, I can do the next level, right? And so on by using this rule. Okay, so let me remind you again. This was the rule over here. It's really actually a very simple rule. It's just taking lambda times the previous one, subtract the next one, the one before that. Okay, so now I've given you a definition of a reduced form, which is for the cusp, which is unique, and I've given you a way to generate all the cusps, right? By going down the ideal Q-gon tessellation. Okay, so let's look at some of the useful properties. Now, if I have a over B is in reduced form for a cusp where AB is not equal to 0, then both A and B have absolute value bigger than 1. In other words, the numerator and denominator for reduced form is basically has to be bigger than or equal to 1 if it's not 0. Okay. If A over B is in reduced form and B is equal to 1, then A must be of the form some integer times lambda. This is a very useful one. If I have two cars X and Y in reduced forms, then this is an even line if and only if A, B, C, D is inside GQ. If and only if the determinant is equal to 1. So this is really the question of Ravi a little bit earlier about how to decide, whether something is an even line or not. Right. So if I give you two vertices, for example, and if I know the reduced form, then I just need to check this whether this is equal to 1. Okay. Any questions? So basically, these are very simple things to prove and very simple properties, but they're going to be useful to build up our understanding of and how we use these things, how we use the Cusp. The next one is also quite interesting and not difficult to prove. So suppose I have a, say, ideal Q-gon. Okay, let's suppose it looks like this. Let's assume that the ideal Q-gon looks like this. 0 or somewhere over here. And then this was a C1, C2, C3 up to CQ, right? Okay. And if I know the reduced forms for them, okay, you don't need to know the reduced forms, but suppose the reduced forms are of the form AI over BI. Then the reduced forms for all the cusps in between C1 and C2, right? The denominator is always bigger than the denominator of C1 and the denominator of CQ. In other words, that algorithm that I give you before for generating the cusp, right? The numbers keep increasing in magnitude. The numerators and the denominators keep increasing in magnitude as you go downwards. This is what happens when you do the Ferry addition, to do the Ferry triangulation, right? Because we're doing, if I have A over B and C over D, then I do the addition, then obviously the one in the middle has bigger numerator and bigger denominator than the two ends. But this is also true in this construction over here. Okay. Like I said, the proof is not really very difficult. Basically, these are discrete solutions of some of a sine graph, okay, and then just have to check it out. Okay. So this property is this lemma. This property is actually very useful in the sense that you more or less can use this to tell whether something is going to be in something is in reduced form, and you're going to be able to tell whether some matrix lies inside GQ or not. Okay, so I'm going to talk a little bit about algorithms now. So having obtained these reduced forms and known some of these properties, we can initiate some algorithms. So in particular, we can find the special polygons for a given subgroup K of GQ if we are able to determine whether something is inside K or not. Okay, so this is based on this fairly simple exercises. If I know x1 and x2 is an even line and y1 and y2 is an even line, and I know the reduced forms, then I can find the element in GQ which maps this even line to this even line. Okay. Because the definition of the reduced form basically tells you how to find the element, how to find the matrix. Okay. Then of course I can also map this to with the reverse orientation, and I can map this to this with the reverse orientation as well. I can also find an elliptic element of order Q which maps x1 to x2. Right? So x1, x2 is an even line. So there's an elliptic element of order Q which sort of rotates it about so that x1 goes to x2. X1 goes to x2. And I can find that element. So all of these things are fairly easy exercises to find these matrices. But once we're able to find these matrices, we can now devise some algorithms. Okay, so let me give 2 examples of algorithm. This was something we did in one of our papers. You can determine whether some subgroup of the modular group is congruent or not. Okay. The second algorithm I'll talk about is you can determine whether something A, B, C, D is which is in PSL2 Z lambda Q, whether it's in GQ or not. Okay, so the first problem, okay, so for some reason unknown to me, the number theorists are particularly interested in congruent subgroups, but there are some subgroups of the modular group which are non-congruent. So sometimes we want to be able to decide whether a given subgroup is non-congruent or not. So what I'm assuming is that I know a special polygon for K, okay? I'm able to construct a special. So in particular, I know a set of generators for independent generators for K. Then there's a theorem, old theorem of Wolfart that says that if K is a congruent subgroup of level M, so K is a congruent subgroup of level M means that it contains gamma M, okay? Then the geometric level of K is also M. So what's the geometric level of K? The geometric level of K is basically the LCM of the level of the width of the cusp of H mod K. Okay, anyway, so the point over here in some sense is that the geometric level of K is easily determined. For example, once we know say the special polygon, okay, that's easily calculated. So if we calculate M, and then since we've calculated M, there's an algorithm now to find the independent generators for gamma M, which was given by Professor Kulkarni in his paper. So then I have a set of so find the independent generators for gamma M. For each of this generator, I'm going to determine whether this generator is inside K or not. And if not, then of course K is not congruent. If it is, then I go to the next generator. Then if all the generators are inside K, then K must contain gamma M, and so K is a congruent subgroup. Okay. So this is actually, so how do you determine whether a generator is of a generator of gamma M is in K or not? This is actually not very okay. So geometrically, what's happening is this. I have a fundamental domain for K. This is a fundamental polygon. I can look at the translates of this fundamental polygon by K, and this gives a tessellation of H. On the other hand, this element over here maps the line from zero, the even line from 0 to infinity to something, right? And if this something is contained in one of the special polygon, is contained in one of the polygons, then it cannot be an element of K. Okay. So the idea is that, so how to do this algorithmically is, if this line over here is in the interior of K, then it is not inside K. But if it's on the exterior of K, it lies on one side of the boundary. And then you can find a unique generator of K, of this, so one of the side pairings, such that this thing over here gives you something which is closer. Okay. So it sounds more difficult than it is. It's just a simple geometric bookkeeping. Okay? It's just saying, okay, here I'm going to find the correct element of K of generator of K that moves this thing closer. And then for the new one, again, I find another generator of K that moves this closer. If at the end of it all, I end up at the line 0, infinity, okay, fine, then it's an element of K. If not, I end up at something in the polygon, which, so you know, it's going to be some matrix which maps 0, infinity to this thing, but at the same time, 0, infinity was not identified to anything inside that fundamental polygon, you see. So in that case, you will not have after a finite number of steps, you can determine whether it is inside K or not. Like I say, it's not very difficult. It's fairly easy to implement this in the code, and I believe that some of the previous speakers have done this. Okay. Determining if something is in GQ, again, that's not very difficult. Let me do this the other way now. Okay, so let me do something like this. Okay, so I have something over here. Let's say A over B, C over D, maybe. Right, so actually it should be, sorry, C over D, A over B, okay? So A, B, C, D maps this line to this over here, right? On the other hand, I have a kind of a tessellation I have a tessellation of the plane by ideal Q-gons, right? So I can try and approach, say, A over B inside using my algorithm, moving, you know, going towards the point A over B, right? So what happens is that if at some point, right, this A over B lies between something over here, let's say x1 over y1, x2 over y2. And if this thing, for example, if this number is less than these two numbers, one of these two numbers over here, right? Then we're done, because you can never get the number A as you go further down. Because things keep increasing as you go deeper and deeper, further and further away from that. Okay, so so you just generate a sequence of you can generate a sequence of even lines in reduced forms converging to A over B, and then as long as at some point this one of these numbers is less than either of these two numbers, we're done. Otherwise, eventually you converge to this thing over here, and you get exactly this. You get exactly A over B. And if you do get exactly A over B, then you go on to try and search for C over D. And so the point here is that after a finite number of steps, actually not very many steps in general, you will be able to decide whether A over B is in reduced form, so or not. And if it's not in reduced form, then the A, B, C, D cannot be in GQ. And then if it is in reduced form, then you do it for C over D, let's say, and then you can check whether A, B, C, D has a determinant 1. Okay, so that's so these are two algorithms that you can do, and there are lots of other algorithms that you can do just using these reduced forms. Right? So remember the key properties of the reduced forms we want was essentially the uniqueness and the fact that we can generate the reduced forms in a systematic way, going away from cusps on even lines, going away from the original even line 0 infinity. Okay. So here the point here is that in a finite number of steps, we can determine whether this thing is an even line or if C over D is also in reduced form. Okay, so I talked the first two parts first on the geometry and then on this algebraic thing. Now I want to bring in something with the arithmetic in the sense that we are a subgroup of PSL2 Z adjoint lambda. So there's an interesting ring there and interesting ideals and so on. So in particular, we can define congruent subgroups of the Hecke groups. Okay. So let me remind you that the principal congruent subgroup of the modular group is defined to be A, B, C, D, such that A is congruent, D is congruent plus minus 1 mod M, and then C is congruent, B congruent 0 mod M. Another way to look at it is gamma M is actually the kernel of the homomorphism of this to the ring, to the 2x2 matrices with entries inside the ring Z over MZ. Okay, so there's also gamma lower 1M and gamma upper 1M. Here, A is congruent. A is congruent to D is congruent plus minus 1. Sorry, mod N. And C is congruent to 0. And in the other case, B is congruent to 0. Okay. And then this one also very important and often used. Gamma not M is where just the lower left-hand entry is congruent to 0 mod M. So all of these are congruent subgroups. This is called a principal congruent subgroup, and these are also different congruent subgroups of level M. Okay, so now let's look at what happens in the Hecke group GQ. So in GQ, I can look at ideals of this ring Z adjoint lambda, and then I can define analogous congruent subgroups of GQ, right? In much the same way. Okay. So remember that before the ideal was actually just the ideal generated by M. So of particular interest is are these two cases when Q is equal to 5, or when Q is odd and bigger than 5, and I is a prime ideal. Okay. Why I say it's of particular interest is because we can actually do something in both of these cases. If I is not a prime ideal and Q is bigger than 5, I guess we can't do anything for now. And so okay, so why is these two cases are interesting? In the first case, when Q is equal to 5, we can leverage on the fact that Q gamma is actually just a quadratic extension. The ring Z mod gamma is a principal ideal domain, and the fact that the set of cusp is actually all of everything is all of the rationals, all of Q adjoint lambda. Okay. So that's the reason why G5 is particularly interesting. In the second case, when I is a prime ideal, then finding the index of GQ over the principal congruent subgroup depends on finding the image of GQ under this homomorphism of GQ to PSL2 with entries in Z lambda over the prime ideal. Okay. So the main thing over here is that this thing is a field. See, if I is a prime ideal, this is a field. It's a finite field of with P to the M elements, and we can actually say something about this. Okay. If P is the prime that sits above I. Okay. So irrespective of this, if I just tell you I want to know something about a given particular principal congruent subgroup, I can also employ the algorithm to find special polygons. So basically, this is the same algorithm as what Professor Kulkarni had for the modular group, but applied to the Hecke groups. Just remember that we had that geometric interpretation, but now we have a way to find all the reduced forms or all the cusps. We have a way to find, to know what the even lines look like. And we have a way to find all the matrices that maps even lines to even lines. So those are the things that we need to be able to initiate this algorithm. Okay, so let me tell you some of the results. I don't really want to go through this too much because this is the part which I'm the least familiar with partly. This is the part mostly done by my collaborators with the algebra and number theory background. Okay, so suppose I have a Hecke group GQ, and then where Q is an odd integer, greater than or equal to 5. 3 is not interesting because we know almost everything already. And tau is a prime ideal of this ring sitting above P, where P is a positive rational prime. Okay. Then we can say something about the indices. Okay, so the index of the principal congruent subgroup is PM plus 1, PM minus 1 over 2. Same answer over here in these two cases. If M is odd, if M is even and this thing is not, and some conditions satisfied. And then in this third case, if M is even and this condition holds, then we have a slightly smaller, the index is smaller. Okay, let me explain what these things are. E is actually is the field ZP gamma Q over tau. Okay, and it has is a field with PM elements, so this is the M, and then it has a unique subfield. If M is even, then there's a unique subfield of order P to M over 2. Okay, so these things here turn out to be. We give you the index, and we also tell you the structure of the quotient group. So the quotient group is actually of the form PSL2E or PSL or PGL2K. There are a couple of other special cases over here. If P equal 3 and Q equal to 5, then the index is equal to 60, and then the quotient group is actually just A5. If P equal to 2, then the index is 2s, and where s is some number which divides Q. So in particular, for example, if Q is a prime, then s is just equal to Q, and GQ over and the quotient group is actually a dihedral group of all the 2s. So these are some small cases, the small cases. But in general, this is the structures here. We also have some results for the other congruent subgroups G1 and G0. So again, there are special cases when tau is above a small prime, and then when tau is not above a small prime, then there are various cases. Okay, so I think for now, it's sort of pointless staring at these results. I mean, this is just some kind of classification theorem which you have to go through. Anyway, but the proof is not coming from understanding the structure of this special 2x2 linear groups over these finite fields. So as a corollary, here we have in the indices of the principal congruent subgroup of G5 of level tau, where tau is a prime ideal, sitting below the prime P are given by these numbers. So when P is equal to the index for the principal congruent subgroup is 10, the index for these two subgroups is 5, which means in this case that these two groups are the same. When P equal 3, then we get 60, 20, and 10. So now this group is strictly contained in this group. When P equal 5, again we have 60, 12, 6. Okay. Then these are the infinite cases. Okay, so we have these numbers. Okay, so let me recap. This is sort of the arithmetic part of the talk. I'm just saying that I have the congruent I have the Hecke groups GQ. Since they sit inside some group whose entries are inside a certain ring, I can define certain congruent subgroups, and then I can ask questions like, how do you know what are the indices and the various geometric invariants of these congruent subgroups? And there are some answers, although the answers are not complete, and they are especially not complete when the Q is not equal to 5 and the ideals are not prime. Okay. So are there any questions on this part? Let me give you some time.
Packages which do any of these calculations?
Sorry?
Any Sage or Gap or
I believe that Mong Long, my collaborator, used to use Sage.
Sage.
Color. But I mean, these answers are actually these are not. I mean, these are actually theoretical answers.
Yeah, sure.
Yeah. I mean, they come from this classification of subgroups of this linear groups, special linear groups over finite field. Yeah, which I think was in the book of Suzuki. Yeah, and I think there's a fair amount of nitty-gritty, count. In this case, what happens? In this case, what happens? In this case, what happens?
For the general Q, the class group must play some role, no? Ideal class group.
Yeah. The ideal class group. Okay, I don't know the answer. It may.
It should play some.
Yeah.
Play some role.
Yeah. Okay, so anyway, but like I say, if you wanted to find a general formulas, you go into some arithmetic. If you just wanted to find a particular concrete thing, you can actually do the algorithm. Yeah, and find a very concrete set of independent generators for a particular congruent subgroup. And here we have a table for all the geometric invariants in the case of, again, this is the case for G5, and we're looking at G05 beta, where beta is again a prime ideal. I mean, I don't really know what to say about these results, except to say that it's quite nice that you can do such a complete classification, and that it's interesting that there are some different cases arising, which means it's a bit more complicated than what happens in the modular group. Yeah, but as you can see, it's just slightly not that much more different, and I think this really just comes from the fact that it is a quadratic extension. Yeah, so the field is not too big. Yeah. Okay, so just very quickly, this is a special polygon for G05 with the ideal generated by 2. And in this case, you see that in this case, what we have over here is this side is identified to this side by this order 2 element. this side is identified this side by some element here like this, and this side is identified this side by one. In this case, it's quite easy. 1, 2 lambda 0, 1. Oh, sorry. This one is just 1 lambda 0, 1, because 1 lambda 0, 1 is in G0. It's in G0 5. Now, if look at this example over here, this is for the prime ideal generated by 2 plus lambda, and in this case, the index is 6, and the special polygon consists of 1 ideal pentagon plus 1 special triangle. And of course, since this is a special triangle, this side is identified this side, then these two are actually identified by order 2 elements, and then there's this thing over here. One more example, let's say the ideal generated by 3, a bit more interesting. There's an algorithm, so which is described over here. You start with this thing over here. Look for side pairings, and then any unpaired side. For example, this side is unpaired. Then we add an extra thing over here, and then we look for the pairings. And it turns out in this case that the index is 10, and the side pairings are given by this picture over here. Okay, so quite interesting is there are still 2 elements of order 2. This side is paired to this side is paired to this side, but there are 2 elements of order 2. And there are actually 3 inequivalent cusps in this case. One of them has a width 1, and the other 3 have width 3. Okay, so and this comes from this tree over here. Okay, let me see how much time I have. I have a bit more than 10 minutes. So I want to go on to the cusp set. So you can see anyhow that the cusps play a very important role, right, in determining, in allowing us to get a hold on of the group GQ. I mean, in particular, when 2 cusps are connected by even line, then we have reduced swarms and so on. Okay, so so one immediate interesting question is, okay, if I denote by K GQ to be the set of cusps of GQ, so this is basically the orbit of infinity under GQ, then what is KGQ, right? So this quite interesting, very classical theorem of Lloyd-Becker says that when Q is 3, 4, 5, 6, 8, 10, 12, KGQ is equal to lambda Q adjoint lambda square union infinity. Okay, so let me give you some time to digest this. For these few special cases, we are able to determine completely the set of cusps. And so let's see what happens in the case of 3. In case of 3, lambda is just equal to 1. So this is just Q and then multiply. So you just have Q union infinity. In the case where Q is equal to 4, for example, lambda is equal to square root of 2. So this thing here is just Q. So what we have over here is just a rational multiples of square root of 2 union infinity. In the case of 6, lambda is square root of 3. So this is still Q, and then we have a rational multiples of square root of 3 union infinity. 5, lambda square is equal to lambda plus 1. So Q adjoint lambda square is just Q adjoint lambda. And then when you multiply lambda in front, this just is still Q lambda. And so we get all of Q root 5 union infinity. So this 3, 4, 5, 6 very interesting. 8, 10, 12, somehow we managed to prove these special cases as well. So you may ask why only these few numbers and not other numbers? So the main reason here is that lambda square is quadratic. over Q, okay, for these numbers. Either quadratic or lambda square is in Q. Okay, so I want to not give you exactly the proof, but give you the lines of the proof because it's quite beautiful. And the proof is technical, but the basic idea is very simple and intuitive. It is just how to generalize the Euclidean algorithm. So what you do with the Euclidean algorithm, if I give you two numbers, two integers P and Q, right? How do I know whether they are in reduced form? How do I know if how do I know that the GCD of P and Q is 1? What I do is I try to, the Euclidean algorithm tells me how to find a new rational number P prime over Q prime, where Q prime is strictly smaller, right? But with the same GCD, and then and you keep going. Okay, and so eventually you end up at essentially one of the numbers is 0, and then if the other number is 1, then the GCD is 1. If the other number is not 1, then the GCD is that other number. Okay. Okay, so let me tell you what the steps are. I'm running out of time, so but the reason why I'm getting quite interested now is I didn't realize this, but this is exactly what I started. I had a project which really is based on this much more recently, in the last few years. Okay, so the first thing is to show that the Cusp set is contained in this. Okay, and this is a very simple. This part is simple. The idea is you just conjugate GQ by this element over here. And why are we conjugating by this? We're conjugating by this so that this thing is conjugated to 1101. Okay. But then the order 2 element is now conjugated to 0 minus lambda inverse lambda 0. Okay. This is just a simple calculation. But in particular, you see that if you want to look for the orbit of infinity under this G, it always stays inside Q lambda square. Because this thing maps something in Q lambda square into Q lambda square, and this thing maps something in Q lambda square into Q lambda square. So in particular, KG is contained in Q lambda square union infinity. Where did this lambda come from? This lambda come from if I move it backwards towards GQ, right? By this original conjugation. So that will be multiplying by lambda. Okay. Okay, so what we really want to show now is that we want to show that the set of cusps is all of this. Okay. We know that set of cusps is contained inside here, but we need to show that everything inside here is actually a cusp. Okay, so I'm giving you a very abstract kind of explanation of the steps. You define a certain level, okay, for things inside here. And that level is going to be some positive integer. Okay. And then you show that for all of these numbers inside here is equivalent to something. Equivalent here means that it is equivalent under the action of GQ of G, okay, to X prime. But now X prime has the same level, okay. So for example, what we do is if I give P over Q and P is bigger than Q, right? I can move it towards into the interval 0, 1. Or into the interval minus half while keeping the denominator fixed, right? Okay, so and now X prime lies inside this interval from minus half to half, and then using this fact that X using the reflection X to X minus half keeps the cusp set fixed. So we can in fact restrict our attention to the interval 0, half. Okay. So in the case of Q equal 3, we have this interval 0, half, and then the level that we choose is actually just the absolute value of the denominator. Then we find subintervals such that which cover this the interval 0, half, such that for every element in this subinterval, I can find an element of G which maps it to some new element Gx with smaller level. So let me remind you what happens in the modular group case. So I have some rational number P over Q where P is less than Q because it's inside the interval 0, half. Then I can use the involution 0, 1, minus 1, 0, and that maps it into something minus Q over P, right? But now P is strictly less than Q, see? And then of course minus Q over P is equivalent to something inside the interval 0, half with the same denominator. Okay, so so that's the simple case. So in the modular group case, we only needed one interval, but in the case of the other Hecke groups, this interval 0, half has to be divided into lots of different smaller intervals, and each of these smaller intervals you have to find an appropriate element of the Hecke group that maps it into a new element to a new cusp with smaller level. And then we are done, right? Because now I start with some element of Q lambda square. I can map into with a certain level, I can map into something with a smaller level and so on and so on. And so eventually it goes to level 0. In other words, it goes to infinity. So the reason why I am emphasizing this is, like I say, I never actually read this paper of Lloyd Becker because it was in German. But a couple of years ago when Alan Reed was visiting me, he told me that this was the motivation behind his work on pseudo-modular groups. And that in fact, and he very kindly gave me his handwritten translation of the Lloyd Becker paper so that I could actually read. And then I realized that, okay, this was the idea that lies behind their ideas for the pseudo-modular group. Okay, so I want to talk now about this question that this thing leads to. Okay, can I find two non-commensurable Fuchsian groups with the same cusp set? Okay, so for example, the modular group has cusp set Q union infinity. Anything which is commensurable to the modular group has the same cusp set. But can I find something which is non-commensurable but with exactly the same cusp set? Okay, so this is another way to phrase the question. Does there exist two non-commensurable lattices in PSL2R with the same cusp set? So for example, is there not a non-arithmetic lattice G such that the cusp set is equal to Q union infinity? So the answer, rather surprisingly, was yes. This was in a paper by Long and Reed, which is now almost 20 years old. They found 4 examples, okay? They found 4 examples. And the way they found the example was, instead of looking at a modular group, now they look at punctured torus groups. So, there was a kind of variation of certain parameters from some fixed parameters for the modular group into parameters for punctured torus groups. And then they exactly employed this idea over here, these steps over here, to try and cover a fundamental interval I by small enough intervals such that denominators were decreased. Okay, so there were 4 examples, and then they asked the question: are there infinitely many non-commensurable lattices with cusp set Q union infinity? So the reason why they couldn't find, the reason why this question was sort of difficult for them was when they did their method, things got the algorithms get more and more complicated and things became very difficult to determine. So it was not clear, in fact, whether there were infinitely many. And in fact, in the paper, they asked the question twice, once in the positive and once in the negative. So there wasn't really a conjecture. It was like, are there infinitely many or are there only finitely many? So we sort of employed the same method, but we had an idea of using a jigsaw construction. So for those of you, I think, for example, sorry, it tells me I'm supposed to stop in a couple of minutes. You may know this construction of Gromov, Piatetsky, Shapiro, right? Of gluing two arithmetic subgroups to get something non-arithmetic. So it's something like that. Anyway, we do something called a jigsaw construction, and then it turns out that by this jigsaw construction, instead of making things more difficult, there were much more generators, but somehow finding these subintervals was very easy. Okay, finding the subintervals that covered so it actually made the problem easier. So anyway, the answer is there were infinitely many, but still the point here is that this idea, these steps over here still applied. Okay. So one of the questions that I've always been interested in is, can I find some lattice not commensurable to G5, which has the same cusp set as G5? Because remember, G5 was rather special. The cusp, it's maximally cusp in the sense that the cusp set is all of Q union lambda. So I kind of like this question because I think it might be, I don't know, I mean, it might be possible to do this, it might not be. Another question I quite like is this question over here. For example, can you determine the set of axes for the hyperbolic elements of G5? So I just remind you that for the axis for hyperbolic elements of G5, what happens is that it forms kind of a periodic cutting sequence for the Faraday tessellation, and hence they are going to be quadratic extensions of Q. Okay. On the other hand, any quadratic extension of Q by a very old classical result, the continued fractional expansion is eventually periodic. And because it's eventually periodic, this means that actually that thing is the endpoint of a hyperbolic element of the modular group. Okay. So in the case of a modular group, this question is completely answered, and it's a very nice answer. But in the case, for example, of G5, right, I think it's just not at all clear how to do this, or for that matter, for any of these other groups which have the same cusp set as, which has the same cusp set as the modular group. Okay, I think I believe my time is up. So my time is up, right? Sorry, Krishnendu.
If you want, you can go ahead for another 2-3 minutes.
No, I just want 10 seconds to say thank you. Okay. Thank you all.
Yeah. So that's great. Okay, that's great, Sir. Yeah, so thank you too for this wonderful talk. So, is there any question from the audience?
No, I think not explicit question, but just a small comment. I think you mentioned about Gromov, Piatetsky, Shapiro's construction of Jigsaw. I think probably the important, I'm not sure, but the important part was that was mostly for hyperbolic manifold, right? Arithmetic hyperbolic manifold, SO in one case. So that was probably one clue that they can, Long and Reed could use it for SO2 one case, which is namely the modular case, like SL2.
Yeah, Yeah, it would be. It would have been true. In fact, to tell you the truth, they never thought about it, so they were quite surprised by our result. And we, I mean, we meaning me and my two students, were not very well educated, so we didn't know about the Gromov-Petesky-Shapiro construction. It's just that after we did it, and I talked to people about this, everyone said, "Oh, that's just a that's like the Gromov-Petesky-Shapiro construction." Yeah.
So it's a slightly different than the ping pong situation, right? Or it's almost same as ping pong, or
it's similar to that. Okay, so what's happening is, in their case, right, you glue along a totally geodesic hypersurface, right?
right? Yeah, yeah.
In this case, this is just a surface. This is just a surface. So you're gluing along geodesic lines. I mean geodesic. So the key difference in our case is, so what we did was we glue many pieces. That's why we call it a jigsaw construction.
I see.
So let me so maybe, for example, you have the G4 and you have G4 and then you have the modular group, and somehow you group G4 and the modular group together. So both of them were arithmetic, but somehow when you glue them together, it becomes something which is non-arithmetic.
So, sir, how you put the arithmeticity? I mean, it follows directly from your construction, or it's some result?
Oh, so it to prove that it's not arithmetic is actually you use this result of Takeuchi. You need to show that there are some traces which are not, because what happens is the trace field in this case is Q, the invariant trace field. So it's just verifying that some condition is not satisfied. So you just need to find some trace which is, for example, equal to half or something like that.
Okay.
It was a very interesting project, this other project, in the sense that nothing seemed clear at first, but things came together rather nicely. So
I see.
Yeah. So anyway, I don't have time to talk about it, but I was just quite surprised that it was linked to this thing which I had worked on. Maybe that's why we could do this, thanks to working on this Hecke groups long time ago. Yeah.
Okay, so is there any more questions? So Devendra, any question on YouTube?
No. Do you have some information about the cusp widths of any of these groups as set of numbers?
Sorry?
Cusp widths. The actual cusp widths.
Cusp width. Oh, cusp width is, so the cusp width is actually, so you're asking for what's the definition of cusp width, or what can we say about the cusp width?
No. The definition is clear.
Have you calculated for certain finite index subgroups of G5 or something? Cusp width?
Yeah. So the cusp widths, in the case of the congruent subgroups, the cusp width is actually, so you're asking for, so okay, so let me give you a definition of the cusp width. Suppose I have a cusp for the surface, right? H mod the subgroup K, right? Then the stabilizer of this cusp inside GQ is some subgroup of one, is conjugate to a subgroup of 1 lambda 0 1, right? So the generator of this is 1 m lambda 0 1 for some m, and so that's the width of that cusp. So one of the questions that, so okay, so maybe I'm not answering your question, but one question I don't know the answer to is, does Wolfard's theorem generalize to, say, G5? So in other words, is the geometric width of the cusp always the same as the, so yeah, if something is a congruent subgroup? if you're asking about Millington's theorem, you know, what kind of cusp widths can or cannot occur, I guess this is a slightly combinatorial type thing. I haven't looked at it very much, but Lang wrote a paper on this, which very clearly written in Journal of Algebra with Lang and Lang, 26, which appeared in 2016. Yeah, so so that's quite a
So they have worked out this cusp width problem of Millington.
Yeah, I think I think he had some kind of a analogous or generalization of Millington's theorem for
They did this permutation representation of GQ, I think.
sorry.
They did the permutation representation of GQ.
Sorry. You're right, yeah.
But I think not Millington's theorem. I will have to check.
Yeah. But I think it's an interesting question, and I think it's a question which seems maybe doable.
Yeah, it seems.
Yeah. I mean, I'm not saying it's easy, but you know, I mean, you can maybe get your hands on it and try and decide what, because of course there are lots of restrictions on what are the combinatorial structure that can occur, right? I mean, the fact that
So the Millington's question was that there was a signature which can be realized or not always.
correct, yeah, that's what they did. Yeah. What kind of signature can arise or not arise? Yeah.
And then in the last, he asked some long signature, including the cusp width also,
Yeah.
and gives the counter examples in modular group case. Yeah, it seems doable in at least GQ or G5, but let us see.
I would say probably, yeah, it's interesting question that maybe you can find the answer. I am so afraid to say anything because, as I say, I haven't really thought about this for 25 years until the last 2 or 3 months when I started revisiting everything. So I'm quite rusty about.
Yeah, it was nice talk actually. However, rusty was.
But I think one thing, you know, revisiting it, I thought, while everything is sort of elementary, it was also rather natural and to some extent fundamental, you know, all these reduced forms and so on. If you are ever going to try and work with these Hecke groups, you have to make this sort of definitions and so on. Yeah.
Okay, so thank you very much, sir, for this wonderful talk.
Thank you.
Yeah.
Thank you. Let me say again, thank you all for inviting me. It's a great pleasure. And thank you, Professor Kulkarni, for being here.
So usually,
and all of the rest of you. Like I said, his paper was really instrumental in my still being around in the math community. And I really thank you.
Thanks. Yeah, so, so thank you very much. Usually we have tea breaks after the lecture.